Hi viewers, welcome to LMS Solution. Today we are going to see about harmonic mitigation in grid-tied solar PV system. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. So here we are going to use non-linear load in between grid and solar PV system. So because of this non-linear load, right, the current quality of grid going to be affected. Okay, because of this non-linear load, the THT is more than 5%. So here we are using around the THT is around 22.24%. So because that means we are using the rectifier with the RL load. So this will be affect the current sinusoidal nature. That means it when we change the sinusoidal nature of the grid current. Okay, when we pollute that the nature of the grid current. So because of that, the harmonic will be arises. It will be affect the other system, or it will be affect the other load also. So here we are going to mitigate this harmonic problem in grid connected PV system. Okay. So for that, here we are going to use control technique, nothing but active current coefficient control concept. So here we are going to calculate the active current coefficient for the load current. So based upon active current coefficient, we are going to mitigate that harmonic problem. So now I am going to explain the system. So this system is consists of PV array. So here we are using PV array. Here we are having 7 series string and 12 parallel string. So each panel having the rating of 315 watts, and then voltage of the each panel, that means maximum voltage and maximum power point is 54.7 volt, and current at maximum power point is 5.76 amps, and the maximum power we are getting from this panel. So here you can see that at 1000 watts per meter square, so the maximum power is around 26.47 kilowatt, and then voltage is 382.9 volts, and for 100 watts per meter square, the maximum power is 2.49 kilowatts, and then voltage is 360.9 volt. Okay, so this is the rating of this PV panel. And then we have the boost converter. So the boost converter is connected between this solar PV and the voltage source inverter, and this boost converter going to be controlled by means of P into MPPT. So in P into MPPT, it receives two inputs: one is voltage of the PV panel and current of the PV panel, and then we have to calculate the current instant voltage and current and previous instant voltage and current, and then you have to calculate change in voltage, change in power. So based upon change in power and change in voltage, so you have to decide the duty cycle. So that will happen inside the P into MPPT. So the P into MPPT will provide the optimal duty cycle in order to extract the maximum power from that PV panel. So this duty cycle is going to be processed via this PWM generator. So this PWM generator will be control this IGBT in order to get the maximum power from the PV array. And then after that boost converter, we have the voltage source converter is going to be connected to the grid and load via this coupling inductor. So this inverter going to be controlled by means of active current coefficient control concept. So in active current control coefficient, right, current coefficient control concept, so you have to measure the load current. So here you need to measure the load current, and here you have to measure the the phase to phase voltage of the grid. Okay, so first we need to convert that phase to phase voltage of the grid voltage into phase to ground, okay, by using this formula. And then next we have to convert that phase to ground voltage into alpha beta quantity. Okay, so first we need to convert phase to phase into phase to ground, and then you have to convert base to ground to alpha beta quantity, that is called transformation. And then again you have to apply alpha beta to ABC transformation, so you have to do that, right? So after applying that alpha to ABC conversion, so next you have to process this voltage VGA, VGB and VGC via band pass filter. So this is band pass filter. So it will be remove some harmonics, that are not harmonic, that mean yeah, it will be remove that high, that mean it allow only particular band of frequency. And then here you are taking the square of this voltage and then adding this, and finally you will get the voltage in the terminal voltage in the grid side. Okay, so after that we are calculating another three parameter, nothing but the WPA, WPB and then WPC. So this is nothing but the unique vector calculation, because so in this method, right, in this control logic we are not using any PLL, phase lock loop. So normally that phase lock loop used for generating the omega t. So omega t nothing but a phase angle with respect to time. Okay, so most of the case we are using that PLL, but here we are not using any PLL concept. So without PLL we are using unit vector concept for synchronization, right? That means synchronization of this grid with the solar PV system going to happen by means of unit vector concept, right? So here we are generating unit vector for the three phases. Okay, and then here you are measuring the load current, and then in this you are going to take the each load, that means each line current, right? And then here we are applying that concept, active current coefficient control concept. So here you have to take ILA, and then ILA going to be multiplied with the WPA, and here we are taking, that means you have to multiply WPA number 2 times, and then you have to take integration, and here you have to take integration, and then you have to divide this one. So finally you will get the active current coefficient here. Okay, so the active current coefficient for line A, line B and line C in the load side you have to calculate, and then you have to take the average. So finally you will get the current requirement, active current requirement will be calculated here. So this is known as active current coefficient calculation. Okay, so and then this IL, so IL will be taken here. Yeah, so here you can see that IL, this IL nothing but active current coefficient. So take will be taken from there. So next you have to measure the DC link voltage, right? So here you have to measure DC link voltage across this voltage source converter, and then it will be compared with the reference voltage. Here we are having reference voltage is 735 volt, and then it will be processed by a PA controller. So it will be generate the DC link current. Okay, so both are added here. So finally we will get the reference current. Yeah, this is a reference current. So reference current, so here it is in form of a DC quantity, right? So that should be converted into AC quantity. So for that we are going to use that unit vector, nothing but WPA, WBB and then WPC, right? So it's going to be multiplied with this reference current, and it will be converted into AC form, and then this is going to act as a reference current. This reference current will be compared with the source current. So ABC nothing but the source current of the grid. Okay, that means grid current. So and then it will be processed via hysteresis controller, So this hysteresis controller will generate the pulse. So here we are getting 3 pulse. So from that 3 pulse we have to generate 6 pulse by taking the inversion of this pulse. Okay, and then it will be given to this inverter. So based upon this current requirement, right, current requirement in the DC link and the current requirement the load side, this overall system will be controlled. And then harmonic, that means because we are using that active current coefficient of the load current, so based upon that we are going to control that harmonic in the system in order to make the source current sinusoidal. Okay, so here we are going to test the system with a different operating condition. So I will explain one by one. So first I am going to command this one. So this is used for creating a distorted waveform in the source side. So I will explain later. So now I am going to make that source that grid voltage is 415 volt 50 hertz, and then here I am going to make initially the solar P, that means irradiation equal to 0. So that means PV does not generate any power, right? So now we are going to test the system. That means here the PV is not generating any power. So now we have only this voltage source converter, right? So this voltage source converter and then DC link capacitor is connected to the grid as well as a nonlinear load. So we are going to just check the response of the system. So I am going to simulate this model. So this is inverter, voltage source inverter, voltage and current, and then I'm going to open grid voltage and current, and then I'm going to open load voltage and current. So grid voltage, current, and then inverter voltage and current, and then load voltage and current. Now I am going to zoom that load current. So here you can see that the load current nature is non-sinusoidal because of that non-linear load. Okay, and then I'm going to zooming that inverter current. So this is a current supplied from that inverter current. Right now there is no solar PV power, right? There is no solar PV power. So because of that that voltage source inverter, so voltage source converter act as a like state com, right? That means, so now I'm going to zoom that source current, that means grid current. So here you can see that grid current is sinusoidal, right? So here the harmonic problem is arises because of that nonlinear load, right? That when we mitigated by means of that voltage source converter, right? That now the voltage source converter act as a like harmonic mitigator. We can call it as a active power filter, right? So when we mitigate the harmonic problem in the load side, so alleviate that harmonic problem, and then that means that voltage source converter try to maintain that current quality in the grid side. Okay, and also I'm going to show you that power level, power of the PV, right? So here there is no power, right? So here irradiation is equal to 0, and then temperature 25 degrees Celsius. There is no power from the PV. That means PV voltage 0, IPV 0, and then maximum power everything will be 0. And then I'm going to open power in the grid. Yeah, this is power of the grid, and then power of the inverter, and then power of the load. Okay, so here you can see that you will see the difference. Okay, so here power, right, power of the grid is negative. So first I will start from the load side. The real power is around 9000 watts. Okay, and then reactive power around 5000 watt, right? So here you can see the power of the inverter. The power of the inverter is real power is zero, right? Almost zero, right? And then you can see that the reactive power is around 5000 watt, right? So the reactive power will be supplied from the voltage source converter, that means active power filter, right? And then here you can see that the real power of the grid is minus 9000 and reactive power is zero, right? So that means grid only supply the real power, that voltage source converter only supply the reactive power, right? So now the voltage source converter is act as a active power filter. Okay, so next I am going to do another condition, that means I am going to make the irradiation equal to 400. Okay, 400, I'm going to simulate this same system, and then we will check the results. So now you can see that we are, that means PV, right? PV operated 400 watts per meter square, 25 degrees Celsius. So because of the, we are generating around 9000, right? 9000 maximum power, right? The PV is 9000 watts, right? So operating voltage around 330 volt, and then current is around 27 amps, right? So next I'm going to open power of inverter, grid and load. Okay, so here I'm going to show that the detail of power in the different area. So now you can see that this is a grid current, right? So grid nature is non-sinusoidal, and then here and then now that inverter, this is the inverter voltage and current. Inverter voltage and current, you can see the current nature is same that of that load, right? That means we are not taking any power from the grid. That means we are not taking any power, real or reactive power. Okay, so here you can see that, so this power, right, is almost zero. Power of grid, that means reactive power of grid is almost zero. So here you can see that, so this inverter power, real power and reactive power. So this is real and reactive power of the load. So now that inverter, right, so inverter supplying the real and reactive power to the load, right? So we are not taking any power from the grid. Okay, so because the PV generating the power, right, so that when we supply the real and reactive power via that voltage was converted to that load. Okay, so now I'm going to change the irradiation, right? So irradiation equal to 1000, right? 1000 watts per meter square. So we will check the EV power. So now you can see that because of changing irradiation, you can see that the irradiation change from 400 to 1000, right? So because of change in irradiation, right, what happened, the PV power also changed from nearly 9000 or 9500 watts to nearly 2.6, right? 2.6 kilowatts, right? So this is a variation of PV voltage and current. So current will be changed from 27 amps to around 73 amps. Okay, so because we are changing the radiation from 400 to 1000 watts, right? So now we are going to check the power, right? Power in the grid, load, and the inverter we have to check. So now we can see that, right? So in this point we increase that irradiation. So now I'm going to zoom this portion. Now we can check the current quality of the grid. Okay, so here you can see the load. In load side there is no change in the load side because there is no changes in the grid voltage, right? So it maintained constant, right? The load current maintained constant. So here you can see that, but now also the load is nonlinear load, right? It will be generate the harmonics, right? So in order to mitigate that problem, so inverter will be generate some compensation current, so not to make this grid current always sinusoidal. Okay, so here I'm going to explain the power of this system. So here you can see the load power is around 9000 watts and reactive power is around 5000 watt. Now you can see that inverter power, right? So because of increasing irradiation from 400 to 1000 watts per meter square, so the power will be increased from 9500 to around 2.6 kilowatt, and then the inverter will supply both real and reactive power. So the reactive power will be, that means load reactive power will be taken only from this inverter, right? And then the remaining power, right, excess power will be is given to the grid. Okay, so when the power, that means solar irradiation, the irradiation will be increased from 400 to 1000, right? What happened, the excess power will be sent to the grid, and then the reactive power, right? The reactive power requirement the load side, so always is taken from that solar PV inverter, right? So then the system will be the grid side, the power factor are always unity. Okay, so this is working with the change in irradiation condition. On same time I'm going to explain the system with the voltage distortion in the grid side. So for that I'm going to make, that mean I'm going to add that fifth and seventh harmonic in the system. Okay, after 0.05 seconds. Okay, and also I'm going to add one voltage source with amplitude of 1.05, and then I will add another voltage source with amplitude of 1.1 per unit, right? That means I'm going to add this thing. If point of common coupling, I'm going to add another voltage source, and then I'm going to create a mm, harmonic effect in the system. So we will check the system performance when we are adding that distortion in the system. Okay, so we have to check the power and everything. Okay, so what happen when distortion occur in the grid voltage side? Okay, so now we can see that, now we can see that, so the harmonic, right? Harmonic will be generated in the grid voltage, right? So even though there is distortion in the grid voltage, right? That you can see that grid current is maintained. That means it maintained at a sinusoidal nature, right? So that means this inverter, right? The solar PV inverter will be maintained. That means it inject the compensation current not to make this grid current sinusoidal. And also you can see that the variation of load real reactive power and the inverter PV inverter real and reactive power. This is grid real and reactive power, right? So here you can see that the load real and reactive power is managed by means of PV inverter, and then excess power will be given to the grid. Okay, here you can see the reactive power is maintained around 0 only. Okay, so for during that distortion condition also, right? So what happened, the current quality of the grid, right, is maintained by means of this by means of active current coefficient control concept. Okay, so next I'm going to test the system with the sag and swirl. Okay, so for that I'm going to uncomment this one. and then I'm going to use amplitude variation. So here I'm going to create the sag and swirl at 0.2 second to 0.24 second, and then 0.3 to 0.34 second. So I'm going to vary the sag, that means create the sag in the grid side at, that means I'm going to reduce to 0.8 per unit, and then swirl will be created for 1.2 per unit, and then you have to check the system performance. So in this condition also grid quality, right? Grid current quality should be maintained. Okay, so you will check that detail. At 0.2 seconds, swirl the sag will be created in the system. So we'll check that detail. So here you can see that the sag will be occur here at 0.2 second, but you can see that the current quality is maintained sinusoidal, but there will be increasing in current, right? So this is because of reduction in that voltage, right? Because of reduction in the voltage, so what happened to the real power consumption of the load? So that will be reduced, and the reactable consumption of the load is reduced, right? So because of that, what happened, right? So the that means power requirement the load side is going to be reduced, right? So then the excess power will be occur in the system. That means there will be excess power in the solar PV inverter. So that excess power will be given to the grid during that sag condition. And also you can see that during voltage swirl, right? That means this is voltage swirl condition. So in voltage swirl condition, what happened? The grid current is reducing. So this is uh, because of increasing voltage. So what happened to the load power requirement? The load real power requirement and the load reactive power requirement is increased, right? So because of requirement, that means power requirement, the load side increases. So that means the power sending to the grid will be decreased. Okay, so that's why that grid current will be decreased. Okay, so this is an operation during that voltage sag and swirl. So during that condition also, that current nature will be maintained sinusoidal in the system because of active current coefficient control concept in the grid tied solar PV system. So this is working of harmonic mitigation in the grid tied solar PV system. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you. Thank you so much. Bye bye.